Good morning, class. Today we're going to be talking about the force due to friction. So friction is something that we live with and deal with. It's a part of everyday life. But let's take a deeper look into the different types of friction and just really the nature of friction and how it works. First, let's look at this book that we have here again, referencing back on this table. As I push this book and let it go, it actually stops. Well, what is it that's stopping it? It's the force due to friction. Even as I'm pushing and accelerating it, there is a frictional force that I can feel opposing my motion. And so friction is this contact force that's interacting between these two objects, and the direction of that force is always in the opposite direction of the motion that's occurring or the intended motion. So again, it is a contact force that is between two different objects, and the direction of the friction force is always going to oppose the motion that is occurring or the intended motion, and it is going to be parallel to the surfaces that are in contact. So when I look at this book, as it's sliding, the force is parallel to the table and the book in terms of its direction. There's an equation for the force of friction, where the force of friction is equal to the coefficient of friction, or mu, times the normal force. So in each situation, there's a different force of friction that can be calculated using this equation. Now this equation actually breaks down into some different variants based on whether the object is either in static friction or kinetic friction. So let's talk about what these each are. So static friction is when an object is not moving, and yet there's a frictional force opposing it. Now right now, why is this block not sliding down this ramp is because there's actually static friction. And the static friction, as we said before, or any frictional force, is going to be opposing the intended motion. It will be parallel to the surfaces. And in this case, we're talking about static friction. Let's take a look at the free body diagram for a second. All right, so looking at the free body diagram, we have the force of gravity that's acting straight down. We have the normal force that is perpendicular to the surface of the plane, coming straight out perpendicular from the board. And then we have the force of friction, static, okay, in this case, because the object is not moving, so is a static frictional force that is opposing the intended direction of motion. Gravity is the parallel component of the force of gravity wants to pull this block down the plane, but it is the force of friction, static, that is actually opposing it. Again, notice that it's parallel to the plane here on the incline, and it is opposing the motion. So this block is under static friction. Let's go ahead and define static friction. So for static friction, it's always going to oppose motion. You will not be moving. And there is a maximum value associated with static friction, which I'll talk about here in a second. Now, as I increase this plane, the object switches from static friction to kinetic friction. At some point, the parallel component of gravity is great enough that it will actually start to slide down the plane. So whether I'm on an inclined plane like this, or if I'm on a flat surface and I'm just literally sliding around, that's really what defines kinetic friction. It is when two objects that are in contact with each other, everything else applies here, except the difference is instead of being static and not moving, I'm now sliding. And sliding is the key. There are objects that when we get into rotation, we're going to talk about objects that are rolling, even the tires on your car, when they are rolling, they're actually in static friction because where the tire makes contact with the ground is not moving with respect to each other. They're not sliding, at least not as long as you're under control. Now, but any block or object that is sliding in contact with each other is when we get into kinetic friction. So let's go ahead and put that up. Okay, so again, kinetic friction is when the objects are sliding with each other. Static friction, again, when they are in contact with each other but not moving at all. And it really comes down to the surfaces that are in contact with each other. Let's get into this coefficient of friction. It's really what it is that's defining it, and it varies depending on the materials that you're using. So, for example, I have this block here, and on one side I actually taped a piece of sandpaper to it. And so it's the same wooden block, same mass, but the surfaces in contact with each other are going to vary. So as I raise this incline, you can see that the block slides pretty easily down. However, by putting the surface of the sandpaper in contact between the two blocks and the board, we have a much different coefficient of friction, such that it's not until I get to this incline does the block begin to slide. So clearly, the coefficient of friction, which is the surface between the two objects, so the material properties of two objects as they're rubbing together. Even this wood on wood may seem relatively smooth, but if you were to look at it at a microscopic level, there really is ridges between the surfaces and irregularities, micro abrasions between the two surfaces. And as these two surfaces rub and interact with each other, that's what's creating this friction. So let's take a look at the differences between different material properties and situations whether we're in static or kinetic friction, even with the same two materials. Let's take a look at this chart. This chart came out of our electronic book and is an abbreviation of a much larger list of materials that you can find online at different engineering websites. But as you can see, pretty much across the board, the coefficient of static friction is always greater than the coefficient of kinetic friction. And so let's look at a couple of these things. Glass on glass, 0.94 versus 0.4 for the kinetic. Ice on ice, 0.1 versus 0.02. Rubber on dry concrete. So this is, in essence, your tires on the road. There's a static friction of 1 versus a kinetic friction of 0.8. So there's a 20% loss there once your tires start to slip and slide. But look what happens when it rains. It goes all the way down to 0.7 and then 0.5 when you're sliding. Again, remember that kinetic friction has to do with the sliding of the material. So this would be where you're turning and you're sliding. The back tires start to slide out. That's when you transition over to kinetic when you're talking about your tires. And really, there's different types of rubber. So the rubber that they use on a drag racing car on a track is going to be a lot softer rubber, much grippier rubber than the rubber that you would see on your all-weather season tires on your car. And now you get a better grip, but those tires don't last as long. So there's a trade-off. So the rubber compound would affect these numbers as well, but you can get a general sense of it. Steel on steel, 0.78. And then Teflon on Teflon. So if you don't know what Teflon is, it's a material, a synthetic material that's made that really is on your non-stick pans that you use, your frying pans that you probably make eggs in, or your parents do. It can be made into a tape, and it's used to like line threads of a bolt. So you'd wrap it around the bolt threads to make it slide in easier. And you can see 0.04. And there really isn't any difference between the static versus kinetic for Teflon. It eliminates so much friction already that it's almost virtually the same. You know, one of the other things that's not on this list is that the human joints I believe, have a coefficient of friction of 0.02. So they're even better than Teflon, which is pretty interesting. And really, you don't want any friction in your joints. And so the way our bodies are designed, there's very, very little friction. So this chart is really just to give you a quick overview of the understanding that the big takeaway is that static friction, coefficient of static friction, is going to give you more grip and create a greater frictional force than once an object starts to slide against another and transition to kinetic, and namely because of this coefficient of friction differences. All right, as you can see from the chart, clearly there is differences in the types of materials when they're in contact with each other. And what was also obvious from the chart is that the coefficient for static friction was always greater than the coefficient for kinetic friction. This is why, and we'll talk about it in a later lesson, why when your tires are in contact with the road, you want to actually keep your tires in static friction. You don't want your wheels to spin out, because that's when you actually lose control and grip of the road, especially if it affects your braking power. To drill down further on static friction versus kinetic friction, there's actually two separate equations that we can use to look at this overall equation here for the force of friction. All right, let's first talk about the force of friction for sliding or kinetic friction. So the force of friction when the objects are sliding and interacting with each other and moving with respect to each other has a specific coefficient of kinetic friction times the normal force. It's what it will be no matter what, always, when an object is sliding with respect to each other. However, when we look at static friction has the ability to oppose motion as much as needed up to its maximum static friction level. At that point, the maximum static friction is all that you can actually accomplish, and then it will actually transition and start to move, and it will become a kinetic friction at that point. So static friction by itself can be up to or equal to the coefficient of static friction times the normal force. If we're typically finding the maximum static friction that we can achieve, it would be the coefficient of static friction times the normal force. So, for example, in this book right here, the maximum static friction is, let's just say for argument's sake, is 10 newtons. That is the maximum amount of force that's required to overcome static friction to get the book to start to move. So if I apply a force on this book of 5 newtons, I'm applying a force of 5 newtons, but the book is not moving. Well, if we look at the free body diagram of this quickly, so looking at this free body diagram of the book, when I'm applying a 5 Newton force, the force of static friction will oppose my force, as it is right here, up to as much as needed. So by applying 5 newtons of force, the static friction will actually counteract that movement by creating an opposite force equal in magnitude up to 5 newtons in this case. As I apply 8 Newton force, there's 8 newtons of static friction. Up until the point where I get to, let's say, 12 newtons of force, I will not be able to go over this maximum level of static friction, in which case I've now crossed over the 10 newtons of static friction, and I will cause this book to start to accelerate because I have a net force differential. So the static friction force allows you and only pushes back as much as is necessary to resist movement up to its maximum level of static friction, which again would be the coefficient of static friction times the normal force. Just to reiterate, for the same two surfaces that are in contact with each other, the static coefficient of friction is always going to be greater than the kinetic coefficient of friction for those two objects. The last thing I want to point out is about the units for this coefficient of friction. We're going to rework this equation to solve for the coefficient of friction. So by reworking the frictional force equation, we find that the coefficient of friction is equal to the force of friction divided by the normal force. And both of those have units of newtons. So you have newtons over newtons. So the coefficient of friction is actually dimensionless. There are no units for it. Again, one last time, right now this block is sitting on this inclined plane. It is not moving because it has static friction opposing its motion of the parallel force due to gravity. And as I continue to raise this incline, the static friction increases. increases until it hits its maximum point, at which point the parallel force of gravity will overcome the static friction maximum, and we would then have an imbalance in forces, and we would have a net force acting down the ramp, and so the block begins to accelerate. At that point is the transition point where we've hit our maximum static friction. It can no longer oppose it, and it crosses over into kinetic friction. And since we now know that the frictional force as it's moving, as it's sliding down, does it still have a frictional force? Absolutely, it has the kinetic friction force, which is going to be a smaller force than its theoretical maximum static friction force that it took to get it to start moving in the first place. Thank you, and I'll see you soon.